Hello ladies and gentlemen, and welcome back to Lecture 10 for GGS 300, Quantitative Methods for Spatial Science. This week we're going to be focusing on the analysis of variance. So assignment 8 will be due on November the 4th, and following that week we will then go into our next week where we have basically the second midterm exam. So there'll be a set of unmarked tests which I'll issue before that in order for you to kind of get up to speed with the type of content that you're going to be tested on. And then once you've completed those, then you'll be in a good position in order to actually undertake the real midterm exam. Let me know if you've got any further questions or queries about any of that, and I'll be happy to chat to any of you. So let's focus today on basically working with 3 or more samples, and the way that we do that, so basically testing multi-sample experiments, is basically by using this thing called the analysis of variance, which is widely referred to as Anova. So you know where we are on here now. We're focusing more on these kind of formalized hypothesis testing approaches. And then within our kind of flowchart that we've covered in previous lectures, we're down here in the bottom right. So basically we have got questions where we're using continuous data. We're looking at differences between the means in multiple different sample groups. And basically for parametric approaches, we'll be focusing on Anova, so the analysis of variance. And then for non-parametric approaches, we'll be using the Kruskal-Wallis Test. So I think this is all reasonably straightforward for you. Obviously, the fact is that in many cases we might be carrying out statistical tests where we've got many more than just 2 samples, and that's why we'd use an ANOVA-based approach, okay, whether that's analysing regions of the United States or regional differences by continent or differences by state or whatever. And really the logic here is that if we've got multiple different samples and we have those sample means, really there shouldn't be any difference from those means if those samples have all been taken from the same population. However, if there is a difference between those means, then we would basically expect that basically these samples have come from more than 2 or more different populations, okay? So we're not able to specifically identify how many different populations. All we know is that they're going to come from at least 2 different populations, okay? So the tests that we'll be carrying out, focusing here just on Anova, the analysis of variance for parametric data, and then the Kruskal-Wallis test for non-parametric data, okay? So in the case of the latter, we'll be focusing there on ordinal data. And in the case of the former, we'll be focusing there on continuous, so interval ratio data from a normal distribution. So in terms of the actual statistical tests that we'll be carrying out, the test statistics for these different tests will always be positive in this case. So we can't use the Z distribution or the T distribution as we've used in previous examples, because obviously they can actually be negative. So here for the Anova, we'll be using the F statistic, which isn't complicated. It's just the T distribution squared, okay? And that obviously produces always a positive result. And then for the Kruskal-Wallis, we'll be using the H statistic, which is just basically the chi-squared distribution. And the chi-squared distribution is just the normal distribution, also squared. So kind of there's similarities in these statistics that we're using here. They've basically been squared, and you're familiar with those underlying distributions that help produce those distributions that we'll be using. So just be aware here, and I'm highlighting this again, that these tests are showing that not all of this, the samples that we've got don't all come from the same population, okay? And we test whether at least one of those samples come from a different population, so that's kind of the driving logic for these approaches. But the tests basically don't tell you how many different populations these samples might come from. It's just saying whether there's a significant difference, okay? And don't worry, I'll show you the limitations of these types of tests as we progress through the lecture today. It's not going to be a long lecture today. I'm just going to be talking through 2 different tests. There's quite a few different steps to those tests, but just a small number of tests that we'll be covering today, not like the maybe 8 tests which we've covered in previous lectures, okay? Just before we begin, I just wanted to point specifically to the benefit of using descriptive statistics and actually visualizing those descriptive statistics before you carry out such a test as an Anova or a Kruskal-Wallis test. So essentially here what I'm demonstrating is that we can show the distributions for the different groups that we might be interested in testing, so these different samples. And then we're also able to explore different types of visualizations, such as these notched box plots here. Okay, so basically this shows a narrowing of the box around the median, as you can see here, the median being the black line. And essentially the notches are a rough 95% confidence interval for the data that we've got around the median. So it's useful as a descriptive pretest because basically if these medians don't overlap, then it's suggestive that there might be a significant difference between these samples, and therefore that would mean that they haven't come from the same population. Okay. So let's get stuck straight into the parametric data assessment, and actually I'm going to break this down into basically six different calculations, let's call it that. Okay, because I've got here 3 steps, but really there's part 1, part 2, part 3 for the first step, part 1 and part 2 for the second step, and then we just have a single calculation for the third step here. Okay, so just think of it in terms of 6 individual things that we're going to approach. So we're going to focus on calculating the between group variability, and I'll explain what that means later. Calculating the total weighted mean of all the samples, calculating the between group sum of squares, and calculating the between group mean of squares. And then once we've completed that first step, in the second step we'll calculate the within group variability. So that involves calculating both the within group sum of squares and the within group mean of squares. And then finally we'll calculate the F statistic. So within Anova, our objective is to compare the means of these different independent random samples, and we have to have at least 3 or more random samples for Anova. And then we have to make sure that they're independent, so they're not coming from the same sample, either places or individuals. And we need to basically have normally distributed data, okay? And we expect within that the population has, the different populations have equal variance, and that this is basically interval and ratio sample data, okay? So for the hypotheses, in the case of the null hypothesis, so the H0 that we've got here, we're assuming that the means for each of those 3 or more groups are the same. Okay, so mu1 for sample 1 is equal to mu2, so the mean of sample 2, and that all of those means for mu k, so that's for as many groups as we have, k is representing the number of groups here, are all basically equal. Okay. Whereas for the alternative hypothesis, so that HA value there, basically what we're saying is that the mu1 value, the mean for sample 1, is not equal to the mean of sample 2 or to the other means that we've got all the way up to mu k, so for all the different k groups that we've got. And then basically we have this test statistic F, and that's what we're going to develop in order to test, and then we get F basically by dividing this numerator here, this between group variability MSB, by this MSW, so the within group variability, which is the denominator. So analysis of variance, what does that actually mean? Well, the sample that we have is called a group, so each sample that we've got is called a group, and basically the within group variability is the total of all of the sample variances that we're going to have. Okay, the between group variability is the variance of the sample means among each of the groups. Okay, so the MSW is all of the variance within one sample, whereas the between group variability, the MSB, is between the samples. Okay, so imagine that we're going to get house price average information for Fairfax City, and then we're going to get it also for Arlington, and then we're going to also get it for Richmond. Basically, the within group variability for Fairfax would be the variation in the house price for that specific location. And that would be the same for the within group variability in Arlington. There would be a specific variation in the house prices that we sample there, or in Richmond. But then only in the between group variability is where we compare the means from Fairfax, Arlington, and Richmond, and we look at how those means differ. Okay, so if the samples are from the same population, ideally the between group variability will be very small, but if they're not, then the between group variability will be very large. Okay, So the null hypothesis here is that the means of these samples are all the same, okay? So there's just one distribution here because they're all overlapping, mu1, mu2, mu3. Whereas over here, the alternative hypothesis is that we basically have these very significantly different distributions, and the means for those are all dispersed, okay? So this might be what we end up with here in this case one, where we only have a small apparent difference, and maybe that's just random variation from the sampling process. So that would be the case that maybe we don't have significant differences between the means, and therefore we would not have enough evidence to reject the null hypothesis. Whereas down here in case 2, we have very large differences, okay? So that maybe is where we have quite significant differences between the groups, and therefore we have enough evidence to reject the null hypothesis and accept the alternative hypothesis. So the steps in the Anova, well, basically to calculate this between group variability, we need 4 components. So we're going to calculate the mean of each sample, this x bar I, and then we're going to need the number of observations in each sample, so that's ni, and we're going to need the number of groups, so the number of different samples that we've got, which is k, and we need the total number of observations across all of our samples. Okay, so if we sample 10 houses in Fairfax City, 10 houses in Arlington, and 10 houses in Richmond, then we would have 30 as the total number of observations in all samples. And we need to get this x bar t value that we have here, which means that we basically need to take the sum for all groups of the number of observations multiplied by the mean of that sample, okay? And that gets us the numerator. And then when we've got the numerator, we can divide by the total number of observations in the sample. So don't worry, I'll go over this in the laboratory session. It should be much clearer to you by then. Then essentially in part 2, we can calculate the between group sum of squares. So to get this, basically we need to, for each of the groups, we need to take the sum of the number of observation in each sample multiplied by that x bar t subtracted from each of the groups' mean of the sample, okay? So I'll show you how to do this later. And then we square that, okay? So we're basically taking the sum of this little equation that we've got here, which I'll be able to show you. And then basically in part 3, all we're doing is we're taking that SSB value from the between group sum of squares and dividing it by the number of degrees of freedom for the between groups, okay? So here what we've got is the SSB as the numerator, and then the denominator is the number of groups k that we've got -1 to get the number of degrees of freedom, and that gets us our MSB value. Then in the second step, we need to get the within group variability. So basically we're doing the same again, where to get this SSW, we need to take the sum for all groups. And then for each group, what we're doing is we're subtracting 1 from this NI, so the number of observations in each group, and multiplying it by the S, which is the variance of the sample squared for each individual sample that we've got. And that gives us our within group sum of squares, and then basically we can calculate the within group mean of squares by basically taking this SSW and dividing it by n, so that's the total number of observations across all groups, minus k, which is the number of groups that we've got, which gives us the number of degrees of freedom for the within group estimator, okay? So this gives us the MSW value, and then all we have to do to get F is we just take the MSB as the numerator, and then we divide it by the MSW value, okay? So here's an example for how we can calculate the actual F statistic that we want to obtain. So for Anova, we need to get the sum of squares for each of the between groups and the within groups, and then the total. We need to get the number of degrees of freedom, and I plotted them out here in a little spreadsheet for you. We need to get the mean squares values, the F ratio, and the P value. Okay. So I've used an example for that number of high school grad rates in the US by region, okay? And this is just a hypothetical example, but it's going to show you that we have by region, so that's the groups, the number of samples that we've got. We have the number of degrees of freedom, so we have 4 regions, so the number of degrees of freedom would be 4 minus 1 here for the number of regions, with the sum of the squares, which is 2,287.3, the mean of the squares, which is 762.4, the F value here, which is 38.56, which is very high, and then basically down here what we have is the P value, which is 1.3, to the minus 12. So it's very, very, very significant at the 95% confidence level. Okay, so as a result, we would reject the null hypothesis and accept the alternative hypothesis in this particular case. Based on this, there are significant differences in high school graduation rates by US region. Okay, and that's not surprising because when we looked at those initial descriptive data plots, we could see that the median values were really quite significantly different. So I think in the western part of the United States, you had very high graduation rates, and then in the deep south and the south part of the United States, there were quite significantly lower high school graduation rates. So this is an interesting result that we found. Okay. So let's just finish now by focusing on the Kruskal-Wallis test. So this is the non-parametric test for 3 or more samples. So here what we're doing is we're comparing the mean ranks of 3 or more independent random samples for difference. So we need 3 or more random samples. We need to have independent data, as I mentioned before, and we would be expecting, as this is non-parametric, that the populations have non-parametric distributions, so non-normally distributed distributions. Also, we would expect here that the observations are ordinal, okay, so not interval or ratio, but you can downgrade your interval ratio data if it's non-normally distributed into ordinal categories, as I'll show you when we get into the laboratory session. Again, the hypotheses here are basically the same. So for the null hypothesis, we're assuming that all the data has been drawn from the same populations, whereas the alternative hypothesis is basically saying that these data samples have come from 2 or more populations. Okay, so we're not saying that it's come from n populations. We're not able to predict that or estimate that. We're just saying that they've come from different populations overall. Okay. So the H statistic here is what we'll be using. So it's it's based on the chi-squared distribution, as I covered previously, and it's basically called the Kruskal-Wallis H statistic. So how do we get H? So we need the number of observations in the sample, Ni. We need the total number of observations across all of our samples, N. We need the Ri, which is the sum of the ranks in sample I. We need G, which is the number of groupings of different tied ranks, and we need Ti, which is the number of tie values within any group. And then what we're able to do to get this H is basically we're able to break this down into 3 different parts. So this first part is the numerator is 12 divided by n, so that's the total number of observations multiplied by the total number of observations plus 1. That's the first part, which we then multiply by the sum of, for all groups, of this Ri squared value divided by Ni. So the Ri is the sum of the ranks squared in each sample divided by this Ni value, which is the number of observations. And then basically what we do is here we subtract 3 multiplied by the number of observations plus 1. Okay, so it's 3 individual parts. I'll cover this when we get into the lab. It's very clear there how it's broken down to the calculations. And in fact, for you to actually understand this single equation here, I think it's actually really useful for you to view in tandem the code that I'll present in the lab. And that's always how I kind of approach this. You know, I mentioned before that not everyone likes just the math being shown, and I quite like also seeing the code, because then I can kind of cross-check my thinking between the two, which is always really handy. And we do have this separate calculation down here if the correction factor for ties needs to be used. Okay, so if we have more than 25% of the ranks being tied, we need to use this additional calculation. So basically the steps for carrying this Kruskal-Wallis test out by hand are that we basically take all observations in k number of samples and we combine them into a single list, as I will do in the laboratory session. The observations are all ranked then, and when we have 2 or more values which are actually tied for any rank, then we just use the average rank assigned to each position. The ranks from each sample are then summed, and then we're able to calculate the H value based on the equations that I just showed you. And then finally we can obtain the P value using that H value that we've produced using the R function P chi squared. Okay, so this P chi squared SQ and then curly brackets. Okay, and you just need to remember the number of degrees of freedom that you're going to enter into that particular function in R. So I'll show you how to do that later. But the Kruskal-Wallis is basically an extension of the Wilcoxon test, which we've covered previously. So just remember that it's non-parametric. So the conclusions are regarding the mean ranks and not the arithmetic means. We'd expect, as we indicate in the null hypothesis, basically that each group has roughly the same average rank. But there are patterns. So with the data that we've used here, so if we're using the regional parts of the United States and we're interested in high school graduation rates, we know kind of a priori that the South is going to end up having lower high school graduation rates, unfortunately. And therefore, if we were to receive a p-value that was significant at the 95% level, as we have here, because this is 6.953 to the -8, well, that would mean that we basically have enough evidence to reject the null hypothesis and accept the alternative hypothesis that these data have been taken from 2 or more different populations, okay? And we kind of got the flavor of that conclusion when we looked at the notched box plots, and we saw that the median for each of those groups, in some cases, weren't overlapping. So the largest kind of contrast was between the West and the South, okay? And this is the type of output that you'll get for your Kruskal-Wallis rank sum test when you run it in R. So you're going to get your chi-squared statistic, which here is 36.1524. If we've got 4 groups, then we've got 3 degrees of freedom, and here we produce that very small p-value, which is indicating that we've got a result here that's significantly different from just if the results had just occurred by chance, okay? So look, it's very short today. I've only covered 2 tests, and I admit some of them go into a little bit more detail and length, kind of more steps than maybe we went through in the previous cases. But these are becoming kind of more complex, but also fewer in the number that we're going to cover, for example, as we cover today. But it does kind of round off what has been essentially the second part of the course. So we had the first part on descriptive statistics. The second part has been on difference tests, essentially focusing mainly on means within samples. And then once we've completed the upcoming midterm exam, which will be not this week, but next week, and you'll have the unmarked tests with them. Once we've completed that, then we'll move on to the final third part of the unit, which will be focusing on things like correlation, and then basically how we use that to actually carry out regression. So we'll cover looking at correlations between 2 individual samples first, statistically testing for those, and then finally we'll focus on things like multiple regression. So that's where maybe you might use any number of desired input variables to understand variability on a single outcome variable, and using p-values to look at the impact of those different models that you can build based on different statistical data sets, okay? So I don't want to take any more of your time. I think that I've covered everything that I need you to do, so I'll see you in the laboratory session. Go grab a coffee, and I'll look forward to seeing you in the next piece. Thanks for tuning in. Have a good day. Bye-bye.